let's go on with the next talk. Next talk is by Shanmugapriya Prakasham, going to talk on black hole hair removal for n is equal to 4 CH model. Shanmugapriya, you have 12 plus 3 minutes. I will warn you 2 minutes before your time. Go on. It's
Okay, yeah, thanks. Let me start by thanking the organizers for giving me the opportunity to present our work in CSGC 2022. My talk is titled Black Hole Hair Removal for N equal to 4 CHL models. This is based on this paper, which we put up in the archive, and it is some work with Subranil Chakraborty, who's a postdoc at CHEC, Suresh, Yogesh, and my advisor, Amita. Let me briefly give you a plan of the talk. We will first start with the puzzle at hand and briefly review the model of interest. Following that, we will construct bosonic and fermionic hair candidates for two black holes. What these two black holes are, we will see shortly. And having constructed these hair candidates, we will see how many of them correspond to actual hair modes. Having the hair modes in hand will lead us to the resolution of the puzzle, which is going to be by hair removal. I will finish up with a summary and comments about some ongoing work. So how do we define black hole hair, and how is it that we even have them in our model? Because John Wheeler famously made the statement that black holes have no hair. And this is what we now know as the no-hair theorem, which states that in the presence of no other matter content other than Maxwell's field, a black hole is completely described by its mass, electric and magnetic charge, and spin. However, for more complicated setups like higher dimensions, presence of form fields and fermions, black hole hair is indeed possible. Jhatka Sen and Srivastava in their 2009 paper titled Black Hole Hair Removal, Nonlinear Analysis, defined black hole hair as smooth, normalizable, bosonic and fermionic degrees of freedom that live entirely outside the horizon. And it is this definition of black hole hair that we will also adopt in our context. Now, having a sense of what we mean by black hole hair, we will see why we are looking for them and why we need their removal. Computations of black hole entropy in terms of the microscopic degrees of freedom are insensitive to the nature of the solution away from the horizon. So this means that if we have two different black holes with identical near-horizon geometries, they should have the same microscopic indices. However, a counterexample of the same was observed in the case of a BMPV black hole in flat space and that of a BMPV black hole in the Dobnut space. So these two black holes, they have identical near-horizon geometries, but their microscopic indices do not match. Banerjee, Mandal, and Sen in 2009 proposed black hole hair removal as the resolution for the above conundrum. Basically, once we remove the contribution to the indices from the hair modes and have the pure horizon contribution, there is perfect matching. Again, in 2009, Jhatka, Sen, and Srivastava explicitly constructed these hair modes. Motivated by this, we will also construct hair modes, and we also propose black hole hair removal as a resolution for the above puzzle for the case of general ZN CHL models also. Now let's look at the model of interest. Exact calculation of microscopic indices with n equal to 4 supersymmetry has seen enormous progress over the years. And for a lot of this progress, CHL models has served as the playground. CHL models, which stands for Chowdhury, Hockney, and Lekin models, are obtained as Zn orbifolds of type 2b theory, compactified on K3 times S1 tilde. Now, for a class of CHL models, black holes can be described in terms of 6-dimensional 2,0 supergravity coupled to NT number of tensor multiplets. So what is the field content of this 6-dimensional 2,0 supergravity coupled to NT tensor multiplets? There are many fields. On the bosonic side, we have a metric, some self-dual and anti-self-dual two-form fields, and many scalars. The fermionic sector contains gravitinos and other Majorana fermions. And the solutions that we will consider are such that all the scalars are set to constant and all the spin half and anti-self-dual two-form fields are set to 0. Furthermore, our solutions are such that they preserve 4 out of 16 supersymmetries. Now let's briefly look at the BMPV black hole metric. So for simplicity, I have just shown you the case of the non-rotating black hole, although all our analysis has been done only for the rotating case. Now the BMPV black hole in flat space, which is going to be called the phi d black hole from now on, is given by the following expression. So in here, the coordinates u and v are given by x5 minus t and x5 plus t respectively. The BMPV black hole in the top nut space, which is going to be called the 4D black hole from now on, is obtained by replacing this flat space part of the metric by this expression for the top nut metric. Now, in these expressions, the functions psi of r and chi of r are two scalars which are given with constants r0 and r4. So the details here are not very important. What is important to note is that these two black holes can be shown to have identical near horizon geometry. Okay, so what is our aim? Our aim is to construct black hole hair, and we want to see what kinds of hair we have and how many of each kind. However, analyzing all possible hair is hard. So supposing we have a few hair modes at hand, there is no proof that only these hair exist. And furthermore, even if all the hair candidates are not known, sufficient hair removal can be done to obtain perfect matching of indices. So this point means that there could be other hair which are equal in number and of the same type for both the black holes. And because of that, they will give rise to equal contribution to both the black holes. Therefore, their presence or absence does not matter for our purposes. So this is what we will do. For the two black holes that we have, we will study only Garfinkel-Wiczewski form field and fermion hair. And we will see whether we are able to obtain a matching of indices. If yes, then we have achieved our goal. So let's start by constructing the bosonic hair candidates. And we will first do the Garfinkel-Wiczewski transform, which is a solution generating technique that adds wave-like deformations on a metric. And so we take a known solution, apply the GV transform, and obtain new exact solutions to the equations of motion. Of course, this cannot be done on all metrics. Our known solution must contain a vector field Km, which is null, hypersurface orthogonal, and killing. And if there are any matter fields present in our theory, they should satisfy certain mild conditions. So the transform, it gives us this new solution G prime Mn from our known solution by adding this deformation T. So in this expression, these scalars A and T are such that T satisfies the wave equation, and T also satisfies an additional condition which ensures that T is in fact independent of the killing coordinate, which in our case is U. And furthermore, the deformation T is such that its V dependence is unconstrained. For the case of the BMPV black hole, the GV transform adds a deformation only to the GVV component of the metric. So a general expression can be given in this manner. Now, in particular, for the 5D black hole, the GV deformation is given by 4 arbitrary scalar functions Fi of the periodic coordinate V, and these are going to be our hair candidates from the bosonic side for the GV transform. For the 4D black hole, the GV transform is represented by this function T tilde, which is given by 3 arbitrary scalar functions Gi of the periodic coordinate V, and these represent the 3 bosonic hair candidates for the 4D black hole. Okay, so this is not all, however, from the bosonic side. We also have the top nut space, which is equipped with a self-dual harmonic 2-form field omega 2n. Now, using this 2-form field, we can construct an anti-self-dual 3-form field, delta H is MNP, in the following manner. So initially, we had mentioned that we have these tensor multiplets which contain anti-self-dual 3-form fields, which had all been set to 0. Now, on those, in each of these tensor multiplets, we can add a deformation delta H is MNP with one deformation for each multiplet. And so with NT number of tensor multiplets, we have NT such deformations, form field deformations. So these anti-self-dual form field deformations will go into the bosonic sector equations, and they will cause some collateral damage. And this calls for a resulting deformation in the metric. And that is given by S tilde. We represent that by S tilde, which turns out to be quadratic in these functions H's of V. So these are some set of scalars that we have. Now, an important point to note here is that these two deformations are not independent of each other because they stem from the same set of scalars H's of V. And hence, form field deformations are going to be characterized by NT number of arbitrary scalar functions H's of V, which correspond to the hair candidates. Now we will go ahead and construct fermionic hair candidates by solving the fermionic sector equations and obtain the deformation psi alpha m. So our fermionic solution is such that psi alpha v is the only non-zero component, and this psi alpha v is independent of u. So solving the equation in this manner, we get two possible fermionic hair, psi alpha v1 and psi alpha v2. And these psi alpha v fermionic deformations remain as valid solutions even in the presence of the Garfinkel-Wiczewski deformations. So this means that these are solutions to the fully back-reacted theory, nonlinear theory. Now, an important point here is that the top-net space does not have any effect on the fermionic deformations obtained. Therefore, for both the black holes, the number of independent arbitrary functions of V are going to be 4 each for psi alpha V1 and psi alpha V2, and it is these which correspond to our fermionic hair candidates. Okay, so now our job is done. We have constructed all the fermionic and bosonic hair candidates that we wanted to construct. But how many of them are actually hair modes? Okay, how many of them conform to the definition of a hair that we gave in the very first slide? So in order to determine this, we need to do 3 checks on our deformations. So first we ask, are the deformations smooth near the horizon? We define suitable smooth coordinates, and then we perform a smoothness check on each of these deformations. Secondly, no additional supersymmetry has to be broken by the deformations. So we ask, is the killing spinner analysis affected? Yes.
Shanmugapriya,
yes.
You have 2 minutes.
Yeah. Okay. Yeah. Thanks. So we ask, is the killing spinner analysis affected by our deformed solutions? So we require that our deformations preserve the exact amount of SUSY as the original configuration. And finally, each of these smooth deformations need to vanish at the horizon. So upon doing these checks, we find our culprits. For the 5D black hole, we find that there is only fermionic hair. However, the 4D black hole admits all 3 types of hair. Now, in terms of numbers, the 5D black hole does not have any bosonic hair modes, whereas the 4D black hole has NT plus 3 number of bosonic hair modes, NT coming from the form field deformations, and 3 of them correspond to the GV modes. And the fermionic hair candidates are equal in number and of the same type for both the 4D and the 5D black hole. Okay, now having the hair modes in hand, let's go ahead and look at hair removal. So what is our question? We want to make sure that the hair modes correctly account for the mismatch factors for each N that we have taken. Now the Zn group action, which is the orbifolding, which is going to be on the form fields. Okay, and these generates twisted sectors with a twist given by a value like this. And here S runs from 1 to N minus 1. And in this case, the untwisted sector corresponds to S equal to 0. Now, very roughly, like I have skipped a lot of details in the calculation, very roughly, let's see how we are able to obtain the mismatch factor f of rho for each value of n by this group action. So for n equal to 2, the splitting of the form fields is such that 19 goes as 11. So 11 of them correspond to the untwisted sector and 8 of them correspond to the twisted sector, which in the case of n equal to 2 is just going to be a twist of minus 1. And we find that these factors, these numbers, they come up as these exponents here in our expression. And upon simplification, we will be able to show that this f of rho is this eta product, where eta is a Dedekind eta function. And this is the exact mismatch factor between the 4D and 5D black holes for n equal to 2. Now for the example, n equal to 3, 19 is split into 7, which is the untwisted sector, 6 of them with a twist of omega, and 6 of them with a twist of omega square, where omega is the cube root of unity. And here again, we get the correct mismatch factor in the form of this eta product. Okay, so what have we done so far? We have explicitly constructed hair modes, bosonic and fermionic, for both the 4D and the 5D black holes. And the main takeaway here was that there are NT plus 3 additional bosonic hair modes for the 4D black hole than the 5D black hole. And we have shown that for each N, these hair modes correctly account for the extra factors and they solve the puzzle. Now, what is our path forward? We are currently looking at some Zm cross Zn models which involve both twisting and twining. And these were studied by Sen and Suresh in 2010. And we are trying to come up with a hair removal story for the above. And this is some work in progress with Abhishek Chaudhary from IIT Bhubaneswar, Suresh, Sutapa Samantha, who's currently a postdoc at Western Washington University, and my advisor, Amitabh. Thank you for your attention.
Okay, thank you, Shanmugapriya, for a nice talk. So now it is open for question. Sriram, you want to go ahead?
Hi, Shanmugapriya. I was just wondering, there was no dynamical analysis. Don't you need to ensure that the hairs don't decay, or is that evident in the situations you're considering?
So basically, we want our hair to have support only outside the horizon. And these are all solutions to the full nonlinear theory. We have checked that. Like once we add the hair modes also, all the solutions remain unchanged.
You mean there are no decaying solutions for these hairs at late times?
I'm not sure about that. Sorry. Yeah.
Okay.
Yeah, Sriram, these are supersymmetric here, so they are not time dependent. So,
But don't you need to, perturb and analyze that they don't decay away? Or it's obvious?
well, yeah, okay. It requires a longer discussion, but so the hair modes we have constructed, they are all time independent.
Yeah. Yeah, they only depend on they're time dependent. Yes.
You mean they are exact solutions for the...
Yeah.
Sorry, Shyam, you wanted to say something.
No, the question is about stability. Solution may be time independent, but the
Right.
Sriram's question is whether it is stable or not.
Yeah, so since they are supersymmetric, we expect them to be stable, but we have not checked.
Yeah.
Okay. Because, the classic theorems like prices and so on will worry about, whether they will remain and look at a time dependent case. Yeah, thank you.
Thanks.
Okay. Any other questions? Okay, if there are no questions, thank you, Shanmugapriya,
Yeah,
for
thank
the
you.
nice talk and discussion.